You still see the right screen?
Yes.
It's on the left, but yes.
So redo the share. See, everyone can have technical difficulties. You're not alone. All right. So double check the stream started.
I was about to punch some Hawaiian music on.
Oh, who wouldn't love Hawaiian music? All right. Well, we are started live to the world out there. I'm Thomas Hall, Executive Director of Clean Start, and this is our Clean Tech Perspective this morning. Our Clean Tech Perspectives are supported by the California Mobility Center, SMUD, Fresno State, the Wet Center down there that does some great product development with farms, River City Bank, one of the leaders in sustainable financing in our region, Bloom Workspaces, where when you come to our meetups, that's where we've got them, and Chico Start, who we're going all over Northern California to talk to people about the energy transition. It's also supported by people out there like you who support us through donations monthly and at our events. You help us hear the validation to why we do this, and I really appreciate it. Now, I'd like to jump into our perspective, who we have Zachary Spencer, partner and chief technology officer of NZT. Now, if you're wondering what that is, I'm assuming that's an acronym for net zero technology. Is that right? Okay, I'm getting a nod. That's good. And he has over 30 years of experience around materials, working with storage, and a whole lot of stuff that I know if I went through the bio that he gave me, it would not really capture how kind of impressive this is. Now I'm going to have his slides, but I'm going to let him take over on introductions on here. I'll spotlight you. All right. So everyone, welcome Zach Spencer of NZT Group.
Yeah, thanks. So yeah, NZT Group, a new company formed here in California, or located here in California, trying to solve basically clean energy type solutions is our main goal. Focused around both hydrogen storage and generation, and then also just energy storage in general. So move to the next one.
See, if I try to do all that,
Yeah, boring. We move on past that too as well. But basically, what it says is that I've had a lot of experience working for very, very intelligent people. I'm a mechanical engineer from South Dakota, and I guess my specialty in life is being able to take what these very, very smart people ideas they have and actually committing it to practice or making it a reality. So that's kind of where my specialty has been over the years, both through like places like Sandia, Livermore, and then just smart individuals just out in the world. So yeah.
Well, excellent.
As I'm sure this is no big surprise to anyone, but energy storage is probably one of the most, with how good solar is getting. Energy storage is going to be really important to both make solar and wind, more and more viable solution for power generation. Obviously, as everyone knows, the sun doesn't shine all the time, and the wind doesn't blow all the time. And so, pairing that with a good storage system, a clean, good storage system is going to be essential, especially here in California, where, I can't remember what the number is, but with such a high level of solar, on the grid, it can cause, disruptions. And the only way to really balance that is through storage. So one of the things I've been working on, again, with some really smart guys is spin. And so what this is a flywheel. And yeah, flywheels have been around for a long, long time, and people have been burned by flywheels and so on, for many different companies, for the past 20 years. But really what's special about this one, why I got involved in this one, is it solves the flywheel problems out there. And what they are is that this maintenance has always been an issue because it runs on bearings, and it's something you got to fix all the time. And that bearing problem, creates vacuum issues and all kinds of stuff, because you have to flywheel to be really efficient. You have to spin it in a vacuum and so on. So what we've essentially done here is create where we're taking the mass and spinning it with zero contact. And so there's nothing that touches it. It's about this one here that you're seeing. It's a 30 kilowatt hour unit. And it's about 700 pounds. So we're lifting that 700-pound mass, excuse me, spinning it and levitating it with zero contact, obviously with magnetics and stuff like that. But what that allows is to get rid of all the maintenance issues that past flywheels have had. And when with flywheels versus normal chemical storage, it's unlimited charge discharge cycles throughout its life. And also with no contact, we're not for sure what actually wears out on this. We think it could be the electrolytics and the electronics capacitors that run out first, which is 20 years from now, because the composites, it's carbon fiber rotor is what it is. And the main reason that is because the strength to weight is really good out of carbon fiber. And as everyone knows, the energy storage is kinetic energy, 1/2 mv squared, where mass is of course important, but the velocity is even more importanter, as you'd say, I guess. So spinning it faster is much more important than gaining weight. Also, because of what it is, it can it can regulate power, so it's very quick to respond. Very low cost maintenance, if not any. And there's no lithium, there's no cobalt, there's no rare earth materials. Even the magnetics we're using are just simple refrigerator magnets, that you'd find on your refrigerator, obviously. And so it's not rare at all, and everything is. I mean, this thing could almost be built at Home Depot. It couldn't, but there's no really complicated or unique parts with this. And also with this, what we'll be able to find is that we're actually cheaper per kilowatt hour than and chemical systems have been going down very, very quickly over the past year. So I can't say that for certain, but at the time when we were doing the cost study, we could be cheaper than chemical storage in the 200s per kilowatt hour kind of thing. And as we go larger and larger, like I said, this is a 30 kilowatt hour system. As we go larger and larger, our economics get better because the electronics stay the same. The only thing that really changes is the size of the rotor to get 30 to 60 or however many kilowatt hours you may want. So, okay.
All right.
What we just specifically designed that flywheel for is to plug into solar farms. Though we can scale it, like I said, to any kind of size. 30 kilowatt hours from what we studied was basically one. Solar farm is made of solar strings, and one solar string can basically generate 30 kilowatt hours of power in a day. And so we want to be able to store all that power, that could generate in a day, and be able to distribute, whenever it's needed. And so that was our initial design, even though, of course, residential systems and so on wouldn't need as much. But again, scaling is not a problem. And you can use this to either time shift power, you can use it to just as far as the fluctuations in the grid from minute to minute or hour to hour. This would also be a good solution for it. And like I said, there's no degradation with any charge discharge cycle. And so, the first charge discharge is going to be the same as the 10,000th one. And so we also see that as a benefit versus chemical storage. And then also we don't have temperature issues. So the cold doesn't affect us. It actually composites anyways, because like I said, it's a carbon fiber composite rotor, generally gets stronger with the colder the temperature. So cold temperatures is fine, hot temperatures is fine. It really doesn't matter. No issues with that versus chemical storage. So yeah. Another thing we've been working on is natural gas and hydrogen storage and transportation. Everyone knows of CNG and LNG, liquefied natural gas. Liquefied natural gas is expensive as far as the capital equipment it takes to put in to liquefy the natural gas to be able to store it. And also, it's done at cryogenic temperatures. And then CNG, obviously, the more you can pressurize, or the higher the pressure, the more gas you can store. So what we've been able to do is find something in between the two, which we call ANG, absorbed natural gas, where we kind of in between the liquefied and the compressed. And why that's important is for everyone has, barbecues in their backyard, everyone uses propane. Well, methane would be a better solution because it's just so abundant and around. It's not a manufactured gas of sort, I guess you'd say. But the volumetric efficiency is very poor of natural gas compared to propane. It's you need about 6 times volume to get the same energy density. So what we've been able to do is with this ANG is to basically make the volumes equivalent from propane to natural gas, or very close. And so that allows for the storage and transportation to be much more a realistic solution. And for example, one of the cases in Indonesia is that they have their own natural gas supply, and that could be from dairy farms or just many different sources of methane or natural gas. And but they don't have anyone to use it because the volumetric efficiency is so poor. And so they actually import in propane for all their residents. And because the price is so high, they have to subsidize all their users. And so what we're able to do is again, allow them to use their own methane and not have to ship in propane, which immediately gets rid of the subsidy that's in place, and also we can get the energy at a much lower cost than the propane that they have. And why part of that's important, though I think methane and natural gas is not exactly a solution. I think hydrogen is a better solution. What we're trying to do with a lot of these countries in Africa and some in Asia is what they're using right now is wood and coal and dung, as their fuel source, which is one of the largest killers on the planet. And so we're trying to give a better solution to help clean that up. But obviously my goal is hydrogen at the end. I think this is a good stepping point to a hydrogen kind of thing. That's a project that we're doing there. So yes, and what we've been able to do is to create the natural gas or hydrogen is create it from biomass, and really where our focus is hydrogen from the biomass. And so lawn clippings to almond shells to rice husks. In fact, rice husks are dangerous to burn because which is what they do in a lot of places, because one of the largest I think rice husks are about 60% silica, and that's not a healthy chemical to breathe in, you might say. And so we can take those and safely convert it to hydrogen instead of people actually burning it. And then as we all know, hydrogen is probably one of the cleanest gases out there. And also we can do biodiesel and other types of fuel too. But again, hydrogen here is the goal that we have to move forward. And so we're looking at putting this kind of technology all over the world. But again, with hydrogen specifically, it's a energy density problem where you see. I was just in the state Sacramento, the state capital, at a hydrogen thing where they had all these semis and so on, and they're carrying 10,000 psi pressure vessels. Well, the benefit we have is we can do a couple of things. We can either take that 10,000 psi, it looks like, and add more hydrogen to it through our technology, or reduce the pressure. And 10,000 psi, as I'm sure everyone knows, it starts to get a little bit uncomfortable as far as safety issues with that kind of pressure. You know, the buses that you see around Sacramento, or I'm sure around the country, they run about 3,000 psi or so. And so we could basically do the same kind of pressure, the 3,000 psi, which everyone's accustomed to, and hold the same amount of hydrogen, you know, as you know, at that lower pressure, which I think is safer to fill, safer to transport, and also the structures, you know, get to be a lot less costly, because, you know, 10,000 psi pressure vessel versus a 3,000 or less psi pressure vessel, it's not just a linear, you know, it's many times less, rather than a linear cost reduction kind of thing. So, okay.
All right. I think that concludes your slides, right?
Sure. Yeah. I hope that was helpful. And like I said, that a lot of this we're still learning and working on. But this is all, again, technology that's in place here in California, and specifically Northern California, that's very close to the point of being able to be deployed, you know, anywhere.
Yeah. So I want to ask some questions around things. One, you had the kinetic storage, the spin energy system, which I remember I think I saw it out at your guys' place, and it's impressive, the having just kind of the floating satyr pushing a floating thing around. And one thing, for people out there, why are the materials important in it? Because if you put in a plastic in a vacuum system, it's going to off gas, it's going to cause issues. And metal likes to things that are spin like to distort a bit, and metal doesn't exactly reform. Was there anything kind of on the reasons on a kinetic system why you have to be really conscious of the materials that I kind of missed there? Or
No, absolutely. So again, like I said, it's you know, kinetic energy is how it's stored, which is 1/2 mv squared. So mass is an important thing, and obviously metal would be very good for the mass, but the problem is the strength is, you know, is about 10% the strength of, say, carbon fiber. And so the strength is what really comes down to be an important part of getting the velocity way up. And obviously, you know, the higher the velocity, the more the centrifugal force. And so metal, being as dense as it is harder to contain. And so carbon fiber or composite is a really good solution for that. Another thing I'll say is that with our system, which is nice, is that everyone's been on an airplane here, I'm sure. But you know, the motor, the engines, the rotors of the you know, the turbines, they have to pull those out and balance them, because after so many hours, they start to, you know, move and shift and whatever. That's just natural, and they go balance them back to, you know, the tiniest of increment of balance. And that's costly, shutting down the system and doing that. Well, with us, since we're not touching anything, we allow the mass to spin around its natural center of mass. And so as it shifts or moves or whatever the case may be, it just finds its new center, and we don't care. And that's totally fine. And so this is going to allow for, you know, much longer life materials, and we don't have to pull this out and balance it or do any of that kind of stuff. It just moves naturally, and it's totally fine. But yeah, obviously composites are a really good choice for this. Now, like you said, with the off gassing and stuff like that, you know, that can be a problem with some plastics or composites or so on. But one of the things that I've done in my past, you know, so many years is work on a lot of satellites and space structures. Specifically for the satellites, important for off gassing, because you don't want that to fog up the lenses of the telescope or whatever it may be. And so we've gone through a lot of studies with NASA and so on to figure out what are the good plastics or composites for this type of application. So we've done plenty of studies, a lot of studies, long-term studies, as to what the right thing is there. And the off-gassing, what that does, the negative to a flywheel, is that even though it's very, very small amount, it causes what's called windage. You operate in a vacuum, but those little molecules that go off will result in a lower efficiency of the whole system, kind of thing. But again, we've done enough studies and work on this that we don't feel that that's really an issue, going to be an issue with this. Now, there are other materials that do have issues, but with the ones that we're using for this specific application, it should be sufficient.
so I know they've deployed some flywheels in, I think, Canada and one of the northern states. I'm there. Are there any flywheel deployments in California around or?
I mean, back in the old days, where I started with flywheels, I started with a company called Beacon Power, and we had several deployments of flywheels in San Jose, I believe, as just a kind of more of a battery backup kind of situation. But no, we're looking to team up and partner with people to start getting deployments out for our system. You know, it's all been basically prototype and proof of concept type of work now.
Okay. How does it, like a seismic activity impact flywheels?
Yep. So with ones flywheels that have axles or fixed on bearings, that's often obviously an issue because as an earthquake happens, you're trying to move that flywheel that doesn't want to move, kind of thing, and so that can cause damage to a lot of system. With ours, we're no contact, and so the flywheel basically stays where it is, and the case itself moves around it. So as long as the amplitude of the earthquake isn't enormous, really shouldn't cause any issues at all.
Okay, excellent. And you were also talking about, storage containers for gas and keeping things kind of under pressure. Um, Talk a little bit about, some of the maybe the difficulties or things you've overcome to keep gases under pressure, to prevent, escaping gases. Because I know, natural gas is a bit easier to contain, but hydrogen is really hard to contain. What are some things that you've overcome or have been able to kind of have breakthroughs on around that?
Yeah, so the main problem is the size of the molecule, and hydrogen is a problem with permeation, and
There's
so
nothing smaller, right?
that's right, yeah, and so um, all the composite tanks that I make, or the majority of them, have what's called a liner. So it has some kind of, as the composite carbon fiber, fiberglass, whatever you might have overwrap, which is what is the structural part of it, and then composites are also kind of inherently porous. And so you have to have some kind of barrier between the gas and the composite to keep it from leaking. And so with hydrogen being with methane, that's easy. So polyethylene or most plastics really work well for that barrier to keep the gas and the permeation rate is so low on something like that, it's not an issue. With hydrogen, it is. And so that's one of the things that we work on. We've been still doing testing here to date is what is the right material for to keep the permeation low. And we can use metals, like a lot of scuba tanks and stuff like that have composite overwraps, use metal liners to help with that problem with the hydrogen. But as we need to get bigger and bigger and bigger to transport hydrogen across the freeways, or interstates, metal liners start to get costly and very difficult to make for something like that. And so we've been working on other materials basically that will have the permeation very, very low, and allow the fabrication of these larger tanks or larger vessels to be a reality.
Okay. And how about for, if you're trying to keep gas under pressure so that to achieve the energy density of another one, how much pressure are we talking about here?
Well, I mean, so like for most, as far as I'm aware, most of the buses and garbage trucks and stuff like that use natural gas, it's about 3,600 or so psi, 3,600. But like the Toyota Mirai or however it's pronounced, and all these semis that are out there using hydrogen, they're all at 10,000 psi. And again, that's a significant difference in energy there. Resistance of containing something at 3,000 psi and containing something at 10,000 psi is a big difference. And obviously, as everyone can imagine, if something were to go wrong, a 10,000 psi explosion versus a 3,000 psi explosion, there's a difference there as well too. And so keeping that pressure as low as you can, but yet keeping the energy density up as high as you can, that's really the challenge here. And myself over the years, I've made things as high as 100,000 psi. Now, I wouldn't recommend that for many things, of course, but we've been all over the place, and it's really that balance of safety versus energy density at the end of the day.
What about, I guess, like durability of these composites versus other options like metal and things like that? So if you put 10,000 psi and make a metal container with it, but it has hydrogen. You can't just use any off the shelf metal because of the temperature and the pressure that it's under. What are some of the things that make, I guess, the material special and work better, and I guess an improvement on what other options?
Sure. So metals metals are good, but they do have their problems, and one of them is I'm sure people have heard about pipelines that once they explode, metal pipelines, it almost creates a zipper effect. For once it starts, it'll zip for miles and create, a lot of damage kind of deal. Composites do not generally have that problem where they don't have a zipper effect where it'll just once it bursts, it keeps going, ripping itself down the way because of just the inherent uh, property of the materials.
That sounds
Also,
terrifying.
yeah, I think it was San Bruno or something like that. They had a problem, I don't know, 10 years ago or something like that. And so we're actually on a, SBIR of sorts to help solve that issue using composites, basically overwrapping the metal with composites to keep that crack propagation, contained kind of thing, if that were to ever happen again. So composites generally fatigue better. Their specific strength and specific modulus are generally better than steels. And so overall, the only negative to composites at the end of the day is the cost. But over the past 20 years, they've come down, so they're starting to be a viable, solution for a lot of different applications. In automotive is generally one that really likes to grind the price down on everything they do. And so you're starting to see, these composite vessels come into the automotive market. And so, they're starting to reach a cost point. The materials are starting to reach a cost point that it's viable for a lot of different industries. And then also, the main thing is the other thing, we worked on a project where we made tanks to haul gas, and versus a metal one, we could haul. It was road limited, so on the road you can only carry so much weight, and so we were able to reduce the weight of the whole truck and trailer itself, where it would carry 25% more gas. And that's significant because basically now you either have to drive less times, or the costing is every basically, fifth trip is free, right? Kind of thing, because you're hauling 25% more everywhere. And so that on every load, and from what I understand, some of these trucking companies they only live off of single digit margins, like 7%, less than 10%. And so having a 25% gain in their payload, that's significant. And so I think we'll start to see more and more of that happen over the years because just efficiency, it's becoming it's going to put a better number on their bottom line. That's where people are going to care.
It also means less trucks, and cryogenic trucks are not cheap.
That's exactly right. That's exactly right. Yeah. And generally, composites do better in cryogenic applications as well too. And so, there's only a certain amount of metals, certain kinds of metals that work good at the low temperatures, like stainless and stuff like that. You can't use aluminum or steel in a lot of those applications, where composites are a good solution for that, as well as the weight reduction.
So yeah, weight reduction, that's huge, especially when we're talking about cars, the energy transition, electric vehicles. You're adding a whole bunch of weight for the battery, which definitely outstrips the weight of the engine that was replaced. So a carbon, or alternative materials are, critically important to that. Where do you see, like, at least for you, the biggest opportunity in energy transition with material science, with what you work on?
I think that there's some new. So I deal in fibers and glue, right? So that's a composite for me, and I don't see them making a whole lot of improvements in carbon fiber strength or properties. Essentially, where I see some improvements potentially on the horizon is again finding ways to lower the cost of that material, and then also I see some new types of fiber coming out that. Fiberglass is considered low strength. However, it's 3 times the strength of steel, right? And it's half the weight or so. And so where a lot of people think it's a low tech material, it can still be a high tech material. But again, its numbers about 300. It's about twice the the strength of steel, or carbon fiber is about 10 times, right? And so there's some materials coming out that kind of are in between there at a very low cost that I see will make some big differences, especially in building materials, kind of thing, because that's also another industry besides automotive where they really try and grind the price down, like any kind of building material. So there's some fibers and some materials coming out that I think will be, again, within the next 5 years, that'll be very, very low cost and a very, very good strength for the cost, which will allow new types of designs and building. And also it could go into the products we're talking about now as well. But the building material stuff, I could see that be a real big plus.
Okay. I know you guys have been in Sacramento for a while, and you're talking about, getting to these economies of scale to drive down price. Is there an opportunity for a large production facility in Sacramento to help on that, or?
I would love to. I mean, all of these projects that I'm talking about, I mean, to me, from my, from what I see, all of these things that we're talking about today here could benefit California, United States, the world, you name it. And California is trying to be the leader of all this. And it seems like they're putting a bunch of money to it. Yeah, we'd love to start here. I mean, this is where the brain trust that I have is here in California, and us picking up and going to North Carolina is not an interest of a lot of us. And so, but again, as everyone knows, manufacturing here in California, they don't make it easy all the time. And so it'd be nice to have some help, at the end of the day, to get some of these products and manufacture this stuff in state, which is where a lot of this stuff is going to be used in the long term.
Mm-hmm. We have some people in the audience here, so I'm going to see if there's anyone that has a question that they want to ask. John, are you thinking about adding a flywheel to your place? Oh, John has his hand up. I'm going to call on you there, John. Go for it.
Okay. Yeah, flywheel is exactly what I'm using. I'm basing my put power systems on the along the lines of Tesla's bladeless. And if you are familiar with it, I was just concerned with the fact that you're talking about your spin, where how many kilowatts are you to generate? 40 for 700 pounds?
30 kilowatt hours, and we're less than 1,000 pounds.
Yeah, I have a 40 kilowatt. If the formula is based on a rule of thumb of 2 horsepower per pound kilowatt to generate a kilowatt, that would mean a horsepower of 100 horsepower will 1-to-1 will be able to power up a 50 kW generator at 2-to-1, right? And I was just going to look for the actual number because it's like a 1.87 or whatever. But I developed a turbine, or built one, a Tesla turbine, and it's based on one of his first ones. It's only 13 inches in diameter. The rotor is 20 pounds, and the whole unit as a whole, I think, might weigh about almost 40 pounds. And if according to Tesla, at 125 psi, it'll drive that rotor to 10,000 RPM, which will deliver 5 horsepower per pound. So that's 100 horsepower from a 13-inch or 40-pound unit. And then what I was looking at doing is applying this tech to get reducers. Belts and shivs is what I'm looking for because they're more forgiving to reduce the RPM from the 10,000 down to whatever a generator would use. Because like on the smaller ones, it's 3,600 RPM, and you can't go more than that or less than that because of the cycle. And then, of course, as you go higher in kilowatts, it reduces because of the size of the rotor or the size of the generator. It needs less RPM, but it needs more horsepower. So
So
I was just wondering with your spin, if the weight is mostly, I imagine, in the magnets that you're using.
It's the magnets account for say it's 700 pounds. The magnets are maybe 150 pounds of it, type of thing. The spinning mass is 300-400 pounds of it.
Right.
and correct me if I'm wrong. The output, though, that's more a function of I guess the motor that's turning the work into electricity, right?
Well,
Rather than
the energy is again is 1/2 mv squared, so it's
yeah.
mass times your velocity, and for us, we're spinning about 22,000 RPM.
But if you
Yeah.
but the energy output is just basically reducing the speed of it, so it's the ability to pull energy out more than it
Yep.
is the weight, right?
Well, I mean, the weight is what the mass
Yeah,
is what
that's the total. That's the energy that it has, right?
yeah, it's the energy, yeah. And so we just have basically a motor that either we put power to the coils and it spins it faster, or we go the other direction where we slow it down and take power out, kind of thing, right? So it's alternating generator kind of deal.
So yeah, okay.
Well, I don't know. My thing was I already blew myself up with the 100 what you call PS, didn't even make 100 PSI for the turbine. Like it said, Tesla said 125 will do, on the rotor of 20-pound rotor will get it up to 10,000 RPM. I had to show what I was going to do. So I boiled some water. My mistake was that I used a pressure cooker and capped all its vents. Like the relief valve was a pressure for the tank, and then the actual, where that little bobble goes on the top that shakes it off. That was my flow pressure. I had a pressure gauge on that to go to my turbine, so I know how much flow pressure I had. And I only realized after I blew up that anything over 17 psi, boiling water, is high pressure. So I'm already shivering here when you're saying 3,000 pounds on the low end. And I'm thinking if that thing goes, if you're anywhere near it, strap or whatever, and especially with composites, you'll have fragments or segments displaced because of a high pressure failure. And I'm getting to a point now that to be on the safe side, because when I blew it up, that was with water, and the other time I exposed myself to anhydrous ammonia that I was going to use for my normal what it would be a thermal converter, and I I almost killed myself because I was exposed directly to the NH3. But I'm going to use hydraulic fluid now. When I've got the 12 volt, 1200 horse psi hydraulic fluid, and then I'm changing everything around, nozzles and stuff to run the turbine based off the compressor of 1200 psi, and then hook that up to an alternator so that I can get the RPM, apply the 12 volts to it so it can deliver the 100 or 100 whatever amperage it's dedicated to, whatever RPM it's spinning, to then feed an inverter where you get all your power from. And then that way I could basically eliminate the some of the dangers of having hazardous hazmat or the fluids or hazardous materials and
sounds like you
exposure
need some
that way.
good composite casing to go around all that.
Yeah.
And
That's really impressive.
Not
Working in that
really.
there too. Well, it's in your
If you're
backyard and
if
you've almost blown up. So
well, that was with
I have not done that,
when
and
I
I like
did
to say I tinker too.
that was with the steam, but I don't. I'm not using steam. That's why I'm going with the running the hydraulic fluid, because it goes in at 100 at 1200 psi and comes out at whatever. It's just drains and just cycle the high pressure fluid between the reservoir and the compressor through the turbine, run the generator, and then out. But then that's all I've been trying to do. It's been almost 40 years now. I'm still looking for money, and that's why I'm trying to go
John,
to
we'll
these
have to have a
things.
perspective where you talk about the Tesla turbine because
Yeah.
I feel like you have a lot more to say on it because you've learned a lot on it.
Oh God.
Definitely, that's one of the things that we've studied a bunch, and part of the DOT testing to get these tanks on the road and stuff like that is actually a gunfire test in some instances. So we take it out to a range and pneumatically fill it, at pressure, and shoot it with a military round and watch it blow up. And so there's a lot of things where
I want that
composites are
job.
much safer than the metal. In some instances, especially aluminum, if there's an ignition source like magnesium, it's gone. And the whole thing is like there's a tank there 1 second, and then there's nothing anywhere. Where a lot of times the composite, what happens is you shoot it, a hole punctures in it, it tips over and lets out the gas. There's no big explosion with it, because again, that has to do with the crack propagation and also with the materials being not able to be ignited. And then also with some of the tests, I believe it's DOT test or ASME test, is you actually have to set your tank in a pan of diesel, and it can't explode for so many minutes, under a certain flame or fire. And they like you to have it leak before it bursts, kind of thing. And so it just leaks out the gas, and it makes a bigger fire, but it's not a big explosion. But yes, definitely we've done both pneumatic burst tests and hydraulic burst tests. And yeah, there is a significant difference, and the pneumatic ones are dangerous. And that's what people are driving around on is they're not filling their tanks up, the methane, the hydrogen, all that stuff. It's a gas, it's not a liquid. And so that's the
Right.
part of keeping things safe and balancing what's the safest way to do this, because these pressurized gases of whatever sort is the future of what's going to happen, I think, for energy here in the world.
Well, well, we all have our own aspects. Yeah, mine was an aluminum pressure cooker that nearly killed me. But it's still, something I got to do. And the only thing I was going to ask is whether I think I asked before Mr. Hall whether or not he knew of any rich single woman who'd be interested in a very lucrative business proposition.
I'll pass them your way.
Okay.
Uh, thank you, John. And I wanted to give you kind of last time to kind of sum up kind of, I guess, what NZT is hoping maybe to do in Sacramento, and then we'll close out.
Yeah, so like we talked about today, we're trying to solve the problems and team up with people to help solve the problems, these energy problems that are coming. Energy storage is a big one that we all know that's happening, and we think we have it because again, no rare earth materials, the lifetime problems are solved, all that kind of stuff, and the cost per kilowatt hour is very attractive. Then the other one is going to be getting a hydrogen infrastructure going, and hydrogen generation. There's a lot of people who come up with good ideas for that. We think we have a really good one, but besides the generation, it's also the storage and transportation of it, getting it to a fueling station or whatever it might be. And with these materials, though we're talking about energy here, again, we're all, it's CO2 emissions and so on. I mean, one of the largest producers of CO2 on the planet is making Portland cement, type of thing. And so we're also working to solve problems there where we've got a much cleaner cement system that doesn't have all the pollutants that happens from it. And so we're trying to solve all these large problems that are coming to a head now throughout the world. And like I said, one of the largest killers on the planet is people burning unsafe fuels, dung, wood, coal in their households, and getting them something that's a cleaner fuel. And yes, hydrogen is the end solution, but I think in some cases there needs to be a small step to get to that type of thing. And so we're trying to do what we can and fight the good fight. And we're definitely always looking for people to help out and help us, because at the end of the day, I'm an engineer. I'm not a good marketer. And that's part of what the NZT group is trying to do with me is try and market these technologies and get them out there. and form these relationships with companies to really make this stuff work and get the solution, because we're not NZT Group's not working on things that are, as they say, tech readiness level 2 or 3. We've got stuff that it's been proven to the point where it's ready to scale up and go and put it to market. So that's our goal here at the end of the day. And thank you very much.
Well, we'll definitely have to connect on try to finding ways to make sure those happen right here in Sacramento.
Love to.
I want to give you a round of applause for joining us today, and thank you very much for that. It's good to hear, an expert or an engineer talk about things, and getting into the details of it is really important. I also want to say, we've got our solar innovation meetup in 7 days. Come join us for that. If you want to hear about cool innovation or want to talk about innovation around it, we have an expert from Utility Drive coming to speak. And we also have Kevin Logue, who talked last time on solar about us. So it's going to be exciting. I always am surprised at how many cool things are happening with solar. We also have our Power Up and Green Drinks, which is that's actually the wrong date, but it is at the end of April on it. So come join us there. And thank you all for attending. And I hope to have, Zach back and NZT back to talk at some point about, scaling up some of these technologies and seeing some projects develop here. All right. Thank you very much. And that's all we had.
Thank you, everyone.
Thank you.
Thank you, everyone. Yeah, thank you. Mahalo. Aloha.